It's all family. Hey, good morning, Cycle 25. And this is yet another talk that we've got. Thankfully, George went and saved the day today with a conversation about wire antennas to be used for the field, something that he's more than a little familiar with, as we all know. This is going to be an interactive session, so feel free to throw questions out there whenever you desire. And we'll get to them. George, do you want to take it away?
Sure. Let me get the right screen sharing here. Hang on one sec.
We will be posting this to YouTube as we do with all of our big talks.
Alrighty.
At youtube.com/cycle25. Go ahead, George.
So my question, Rod, is do you see slides?
Oh yeah, PowerPoint's up.
I see PowerPoint. Yep. And I see slides.
We'll go back to this mode here. All right, okay. Very good. So this talk, I've done this talk a few times. It's really two different topics kind of morphed together. So the whole topic is around portable wire antennas for HF, particularly for things like SOTA, POTA, or anything along those lines. There's two parts to it. One part is some basic antenna theory about these kinds of antennas, which always gets a lot of dialogue going about how these things work and how you should deploy them. The other part of it is my personal experience of how I came about to work on this project to begin with. So I'll start out a little bit about how I wound up working on this for my own interest, and then we'll talk a bit about the antenna theory. So ask questions as we go. So let's start with what really motivated me to work on this to begin with a few years back. I really like portable operating. My very favorite thing in the world for ham radio is field day. And last year, as John, KJ6VU, now I remember your call, John, knows that we love doing field day, and last year was really difficult because we didn't. We did it from home. So anyway, I like portable operating, which is field day or camping or hiking or whatever. And so for me, size and weight is really paramount. I've lugged a lot of big heavy things to field days in the past, and as time goes on, the less I want to do that. And so size and weight are really key. If you're doing portable stuff like backpack portable, then it's absolutely critical. So so those are big considerations. So for local portable operating, this is like the typical trail here in the Bay Area. This one in the Santa Cruz Mountains happens to have a park bench picnic table on it, which was really a surprise after going in on the trail about 1.5 miles to have such a luxurious place to sit. And a few years back, my typical portable station is a KX3 and a lithium iron phosphate battery, and using a wire antenna, some lightweight coax, and then a wire up into the tree. Since then, I've gone down to the KX2 for really portable stuff, and lately a IC705 when I feel like carrying a little bit more weight and want the luxury of a big screen. But whether you're day hiking or backpacking or whatever, portable is really important. So when I decided to start working on this antenna project, I had two inspirations. One was my absolute favorite field day antenna that we've used for many, many years is a wire vertical. So it's simply a fiberglass pole with a wire as the radiating element. And at the base of the pole, we put a plastic box that looks like an ammo can. And inside that plastic box is an SGC random wire tuner. And then we lay out about a dozen radials on the ground and pull the coax to the station. And this works on any band. You can set the antenna up in about 5 minutes or 10 minutes, and it takes about 5 minutes to pull it down. And so it makes for a great portable antenna. It's not small enough for backpacking, but for portable operating and quick and easy setup, we thought it was a great antenna. So that was kind of one thought, how to use something along those lines. The second thought was to really put on your backpacker hat and think, okay, how would a backpacker approach this problem? And there's a guy named Ryan Jordan who wrote a book about backpacking. It's called Backpacking Light. And I thought his points of philosophy were very well taken for portable radio operating. So his point essentially is weigh everything, eliminate things you don't need, watch the ounces, the pounds take care of themselves essentially, and come up with a system. This is really applied to backpacking in general, but I sort of took it to heart for the antenna design. So the goal for the antennas was to absolutely minimize the weight and the volume of the antennas, because in the extreme case, when you're backpacking, every ounce matters. So you don't really appreciate this until you start lugging it around. And if you're really a neurotic backpacker like some of us, you snip the labels out of the back of your shirt to save weight. So that's sort of the mental frame of mind I had in approaching this problem. Okay, so the design goals for the antennas, first of all, you really want to have full size, efficient antennas. Why? Because if you're operating portable, you're operating low power. And if you're operating very portable, like backpacking, you're operating 5 watts, more or less. So if you have a inefficient antenna, you're just losing energy in your antenna system. So on one side, you want to get the largest full size possible antenna you can get away with. You want to use really lightweight components. You want those components to be very robust so they don't easily break. Ideally, a modular system, kind of in keeping with Ryan's philosophy. You really want it to be easy to set up. In the extreme, again, if you're backpacking, you get to your destination, you're exhausted. You really don't want to spend an hour setting up your stuff. If it takes more than 5 minutes to set it up, you're just not going to do it. So this is true for me personally. If I went to the park, if it takes me 2 hours to set up the gear at the park, I'm just not doing it. So quick setup is really important. So my goal was to be able to get on the air in 5 minutes. That was the target. If I can't do that, then I'm probably just not going to do it. So there are 2 fundamental design decisions that were made pretty early on. The first is the only radiating elements that really fit the bill based on my requirements were to use full-size wires for the antenna itself. Why? Because wire is really lightweight and wire is really compact. And if you have enough of it, you can have a full-size antenna, which is very efficient. The second thing is, and this is really the trigger that set this whole thing off. Several years ago, I found a company that made a fiberglass telescopic pole that would telescope out to be 10 meters in length. And when you collapse it down, it collapsed down to 26 inches. So this is really the enabler. This was really the thing that made all the difference. You could go out and find all kinds of fiberglass poles like kite poles, Jack Kite's a very popular brand, and they're very good. But when you collapse them down, they're about 3.5 to 4 feet long. So that really makes it unwieldy to carry. There's a ton of fishing poles, crappie poles, that sort of thing. But most of them are about 15 to 20 feet. So if you're just going to operate 20 meters, maybe that's fine. But as soon as I saw this 10-meter long fiberglass mast, I thought, wow, that's a magic number, because that's a quarter wave on 40. And for me, the 2 money bands are 20 and 40. So if I could come up with a system that worked 20 and 40, then that would be awesome. Especially if you are hiking, a lot of times your operating time is in the evening, and 20 may not be great in the evening, but 40 will be reasonably good. So that fiberglass pole was kind of the real trigger. Now, if you have wire and you have a mast, you can make all kinds of antennas. You can make a dipole. Well, it's hard to have 2 supports, but you can make an inverted V. You can make a sloper. You could have an Nfed wire. You can make a vertical. You can make a ground plane. You could do all kinds of stuff. So that seemed like it was a pretty flexible approach. So what I wound up making is a whole series of feed points, because there's no one perfect antenna. Different antenna designs have some trade-offs. So ultimately, I made 3 different antenna feed points. There's a dipole feed point, which is the first one there. Typically, you deploy it as an inverted V with a single center support, because you don't have 2 ends. And that's perfectly convenient to do. The second one over the yellow one is a 9-to-1 unun in that package. So this is a random wire antenna that requires an antenna tuner. And then the third one is a 49-to-1 unun on the feed point, and you measure out a half wavelength. So it's a half wavelength Nfed antenna. We'll talk about the pros and cons to all these antennas in a moment. And then the last thing is an accessory, which is an inline choke. This one you can see exposed there. It doesn't have the shrink wrap around it. From a construction point of view, what I decided to do is to build the feed points on a piece of PCB material. So this is FR4 fiberglass. circuit board material. Why circuit board material? Because I know how to make circuit boards. So since that's the thing I know how to do, that's how I made it. If I were a woodworker or a metal guy, I would probably use a lathe or a bandsaw or something else. But since I know how to make a circuit board, everything comes out looking like a circuit board. Now, it turns out that was actually a decent decision, because circuit board material is very rigid, and if you get thick enough stuff, so all of these are made on extra thick FR4. Normal circuit board material is 1.6 millimeters thick, and these are all 2 millimeters, and you'd be surprised what 0.4 of a millimeter will do for you. So it makes these things very rigid and stiff, so that it makes them more robust. So we'll talk about kind of the pros and cons of each of these antennas. Oh, the other thing on the construction is a lot of these kind of antennas are built into a waterproof housing, like a plastic box. And the downside to that is that they tend to be bulky, and they tend to definitely be heavy. And so I opted to go for smaller volume and lighter weight rather than waterproofness, because since these are portable antennas, you're not putting them up and leaving them outside all year long for years at a time. So you're only going to string it up while you're operating. And so, and by the way, if they got wet, and a lot of people, take them outdoors and they do get wet, with the shrink wrap around the feed point, it eliminates the abrasion on the wiring, but it does let air flow through. So while they're not designed to be used outdoors in the wet weather, they'll dry out really easily. So it's really not a problem. I just wouldn't leave one out permanently. I do have a bunch of people who've bought them for home use, and they just stick them in a plastic box. They'll stick it in a sandwich carrier and poke a drain hole in it, and it'll work fine. But that's not really what they're originally intended for. These things have become surprisingly popular. I've got a groups.io page with about 600 people on it, which is a shocker to me, to be perfectly honest. I thought there'd be like 5 people that would want this, and it turns out that a lot of people wanted them. So we have them manufactured commercially and sell them. And so we've had a little review in QST magazine. There's a ton of videos on YouTube of people that have used them. So Stuart Thomas, KBU1HQS, who is #1 in National Parks on the Air a couple of years ago, it's his main antenna system that he uses. Mike K8MRD has a bunch of videos that are really a total hoot. He's really exciting to watch operate. He's very enthusiastic. Julian OH8STN has used these things, et cetera, et cetera. So anyway, go on YouTube and you can just search for Pactena. You'll find a whole bunch of folks who've used them. This is the picture that I got a week ago, and this one just blew my mind. So this is a guy who is a skydiver, and he's at 11,000 feet. And what he's doing in this picture is he's paying out a leader line, which eventually will connect to the end of the antenna. This is an Nfed halfwave. And so he's making contacts while he's skydiving. And so this was a test run to look at how the wire will pay out. And he was trying to get the wire to be horizontal while he's plummeting earthward. And so he was looking at, do I put a weight on the end of the wire, or what do I do to keep the right orientation of the radiating element? So this is just an amazing picture, and there's more to come. And he's going to be writing up some sort of article or something on this. But I just absolutely love this picture. So one thing that I want to stress when it comes to these antennas, there's no magic in these antennas, in the sense that everything in the antenna design itself, the electrical design, is well understood. This is stuff that was documented in the handbook 70 years ago. So it's not like we've invented a new antenna. We've determined there's a new integer between 5 and 6. No, there's no surprise invention. It's just more the packaging of a tried and true antenna design and understanding really how to use them. That's what we've been focusing on. So you could deploy these things in a variety of ways. The first idea was to do a dipole, or really an inverted V, using that fiberglass pole as a support having the feed point up at the top and then having the wire elements. The way I construct the wire elements is since I really want to operate 20 and 40, I cut the wire elements to be resonant on 20 meters. So they're quarter waves on 20, about 16 feet long. And in a link dipole configuration, you could string them in series and put 2 quarter waves in series, and then you can have a mechanical link that bridges them. And that lets you operate that antenna on 20 and 40. The beauty of the inverted V is they're horizontally polarized antennas, which means if you're in a noisy environment like an urban setting, so like here in San Jose, it'll be a quieter antenna than a vertical. So that's a plus. It's also pretty easy to change bands. You just pull the center down and make the links and hoist it back up, and you're on the other band. And the wire elements do act as guys as well. So really decent antenna, pretty easy to deploy. The only downside is that it does take more space on the ground. So if you're in a campsite and you have limited space, then you might not want to use this because you have to have about 20 feet from the mast out to the end of the guys. And you do want to keep the ends of the wire elements about 3 feet off the ground or more. Otherwise, it'll detune the antenna more as you dip the ends of the antennas closer to the ground. So that's like a very typical approach. This antenna is also great for any antenna or any radio without a tuner, since they're resonant. One of the big advantages of a full-size antenna that has no loading is that they tend to be fairly broadbanded. So in other words, if you cut the antenna for the middle of the 20-meter band, if you go to the edges of the 20-meter band, while the SWR will go up at the edges, it's not going to go up a lot. So if you tune it to the middle and you have an SWR of, let's say, 1.3 to 1, which is really low, when you go to the band edges, maybe you're up at 1.7, maybe worst case. It's probably not even that bad, which means you can go across the entire band without a tuner and you're perfectly fine. If you look at a lot of the commercial antennas for portable use, they tend to be mechanically shortened antennas because they're trying to compact the antenna. So you get a lot of linear loading. When you do that, you shorten the antenna mechanically, which is great. But when you do that, you increase the Q of the antenna. So it becomes a narrower antenna, so you have to tune it. So that means you have to fiddle with the antenna. With these antennas, you set it up and you're done. There's no adjusting required at all. If you have like a vertical antenna with a big coil in the middle, you have to move the tap around and get the right spot, which is not a big deal, but it's more to do. And also that coil is heavy, so it comes at a penalty. When we make the wire elements, what we do is take the wire, measure it out, and make a loop on either end, and use these plastic clips to connect the antenna to the feed point, or to connect the elements together. So all the strain is carried by the wire and the clips, and the actual connection, the connection between the links or to the feed point, is done with gold-plated banana connectors. You could use a whole host of different kinds of connectors. I chose these connectors largely because they have a high surface area and they're gold-plated, so they're good for RF applications. They're very easy to install, and you can also mount them very low profile on the circuit board itself. So that turned out to work really well. This picture shows some fairly large wire. This is the first version of the antenna. Since then, I've replaced all of the original design with what we call the mini version, which uses 26 gauge wire. It's a steel core with copper on the outside, 19 strands of wire, 26 gauge. So it's got a pretty strong test, but it's very, very small and very lightweight. This is what the links look like. So the little ferrules there, this is a prototype, but the ferrules that are used to do the crimp is a longer sleeve, so it gives you more purchase. And then you can see the male and female bananas slipped together with a little bit of heat shrink for strain relief on the wires so that they don't snap. You could also take the same kind of notion and make a ground plane like on 20 meters with a 10 meter mast. So you can put the feed point in the middle and run a quarter wave up and then radials if you really want to do a resonant quarter wave. So those are just some of the kind of configurations you could do with an inverted V, but much as I like the inverted V, I use the Nfeds more frequently, and they're by far, I wouldn't say by far more popular, but they're certainly the most popular antennas. When I got my license back in the 70s, I didn't know anybody that used an Nfed antenna. Everybody used resonant antennas like dipoles or beams or whatever. Nobody used an Nfed, probably because you're in the city, you don't have a lot of land, and you don't want to cause RFI, and there's a bunch of considerations around that with these kind of antennas. So today, however, Nfeds are quite the rage. And I think there's a couple of reasons. One is portable operating is super popular, and they do lend themselves well to portable operating. They're very cheap, very easy. You can easily build it yourself. You don't have to buy a commercial one, and they're fun to play around with. But it's kind of important to understand feed point impedance of these antennas and why you use one particular type of Nfed or another. Before I jump into that, I want to take a quick pause and see if there's any questions. Excellent. Thank you for no questions.
All right. I have a quick comment if you'd like.
Please do, John.
I like the fact that you stress full-size antennas for portable, because the one factor that's present there in a full-size antenna, where you have a fairly high radiation resistance, your efficiency stays up. You can use smaller antennas, yes, by loading coils and other things, but the efficiency goes down rapidly, particularly in a small antenna.
Yeah, I couldn't agree more. In fact, one thing that really I get a chuckle out of, you see a lot of guys who start in portable operating, and they'll get an antenna that is, let's say, like a little 2-foot base and a loading coil and like a 4-foot whip, and they'll put it on 40 meters, and they'll set it on the ground. So it's like, okay, what else could we do wrong with this picture? Will your antenna will it resonate? Yes, of course. So the transmitter will be perfectly happy, but it'll be a super inefficient radiator because you're talking about something that's a small fraction of a wavelength in size and mounted on the ground, so you have big ground losses. Oh, by the way, they might go so far as to stretch out 1 or 2 radials on the ground, which, anyway, and then let's operate 5-watt single sideband and be frustrated with why we can't make a contact. You're just stacking the deck against yourself, and so that's what I'm trying to get people to avoid doing. So,
hey, George,
yeah, go ahead.
Sorry, it's Ian. Can you go back to your slide where you turn that into a vertical configuration?
Yeah.
Because one of the challenges I face is, being in a campsite is limited space.
Yes.
So, I'm always thinking about, and I've tried, the Hustler whips with limited success because, all the reasons. And I just wanted to sort of see that one again. Have you tried this and have you had success?
Sure. Yeah. It works great. Now, the only problem with this is not a space efficient antenna. Because if you, first of all, you can really only do this with 20 meters and up in frequency because of the size, which is okay. But if you did a 20-meter ground plate, then you're going to put 3 guys out, and those guys are going to be probably 15 feet from the center point. So now you have a 15-foot radius, which is inconvenient to say the least.
Yeah. No
so
kidding.
I'll show you what I would do if I were you in the Nfed section here.
All right, sure. Yep.
So let's talk about impedance. This is something that either you really know and understand it because it's really basic stuff, or you have no idea, and it's very illuminating if you've never really walked through this. Some very, very simple facts around feeding your antenna. So as John's taught us before, when we talk about feed point impedance of antennas, a half-wave dipole, we think it's a 50 ohm antenna. It's not a 50 ohm antenna. A half-wave dipole is about 72 ohms. But our transmitters, being 50 ohm transmitters and 50 ohm feed line, close enough. It's even without a tuner, you're not going to get a lot of complaints. You can trim the antenna and you're fine. But anyway, you're looking at around 70 ohms or so. If you start to move the feed point of the antenna towards the end, the impedance starts to go up. And so the further you move the feed point, the higher and higher the impedance goes until you get to the very end of the antenna, at which point you're at the highest possible feed point impedance, which is somewhere between around 3,000 to 5,000 ohms, which is pretty high. That's quite a bit different from your 50 ohm transmitter, what it wants to see, right? So you've got 2 problems when you do an Nfed antenna. Problem number 1 is the impedance is off by a significant amount, and the second problem is, what happened to my counterpoise? When we think about the dipole, it sort of makes sense because the center conductor goes to 1 quarter wave the shield goes to the other, you have a balanced antenna. So that makes sense. But when you come down to the Nfed, what happened to the ground side? What happened to the counterpoise? And physics is going to figure out a counterpoise whether you wanted it to or not. And so you need to understand what actually happens with that. So 2 problems to solve. One is, how do I bring down the impedance? And that's pretty easy to answer. You need a transformer. And then the second thing is, what about the counterpoise? And depending on a bunch of factors, this may work well or not. And we'll talk about that. So let's take a look at these 2 different popular kind of antennas. One is the random wire antenna. So what's the basic theory of the random wire? The basic theory of the random wire is that it's not resonant on any frequency that you're operating on, which fundamentally sounds crazy, right? Well, why in the world would I want that? And the idea is that you're going to apply inductance and capacitance to feed the antenna to match the antenna to the impedance of the transmitter. The reason it's not resonant is because if the antenna were resonant at a half wave, let's say, then the impedance would be really, really high, and you have to compensate a significant amount with inductance and capacitance to bring the antenna to match the transmitter. If you're lucky and you're a quarter wave, then no problem. But if you really want to have a reasonable chance of matching the antenna, you're better off bringing the antenna impedance down a bit to begin with. So hence not a half wave. And so a random length. So this does mean that you have to have a tuner. So if you're using an Elecraft KX2, for example, it's got a marvelous tuner built in. It'll tune this kind of an antenna, no sweat. If you have a typical radio with a tuner, most radios like I was about to say an ICOM 7300, but even that has an exception. The normal mode of a 7300 has the typical tuner. Those built-in tuners have an impedance range of somewhere between about 25 ohms to about 150 ohms. So it's essentially like a maximum 3-to-1 mismatch tuner. They're really intended to trim an antenna that's kind of in the band to begin with. If you need to go to a wider range for an antenna like this, you really need a tuner with a wide tuning range that has more like a 10-to-1 SWR tuning range. Something between, let's say, 20 and 800 ohms of impedance roughly is very typical. Those are made by LDG, for instance, or MFJ, or there's a variety of little guys that make tuners that are intended for these high impedances. But even those tuners have a maximum impedance they could tune of somewhere under 1,000 ohms. So if your random wire antenna is, maybe it's not 5,000 ohms, but if it's 2,000 ohms, you still have a ways to go. So what you can do is put a transformer at the end of the antenna. So you put a 9-to-1 transformer as an example, and it'll transform the impedance from whatever it is down 9-to-1 to something lower. So if you have, let's say, a 4,000 ohm antenna, you put a 9-to-1 transformer, it's going to come down to 500 ohms or thereabouts. That's well within the range of what any wide range tuner can handle. So a 9-to-1 transformer plus a wide range tuner, you can actually operate on any band. So if you want to operate any band, put up one antenna, super simple, this would be the way to go. You could use any length of wire. You just want to avoid a half wave to make it a little bit easier for the tuner. And down at the bottom, you can see some lengths that I noted there that are very typically used: 29 feet, 35, 41, 58, 71. The reason those are magic numbers is that if you look at a half wavelength on any amateur band in the HF spectrum, those lengths are not a half wave multiple for any band. So those are safe without thinking about it. If I had 41 feet of wire, it will never be a half wave on any of the amateur bands. So if you're only operating on one band, you just need to avoid a half wavelength on the one band, and you're fine. But if you really want all band coverage, you want to pick one of those lengths. For me, for portable operating, the quickest, certainly my favorite backpacking kind of antenna, but even still, for quick operating, my favorite antenna would be a 29-foot wire with a 9-to-1 going to a radio with a tuner. The reason is that if I have my 10-meter tall fiberglass mast, I could put up a 29-foot piece of wire vertically and put the feed point near the base. And I have a very, very small footprint. So if you want to, like Ian, if you're talking about a camping antenna, that would be the simplest, smallest footprint, broad, any band antenna to use. Now, it's slightly less efficient than a resonant antenna, but it's probably, depending on the band, it depends on a lot of things. You're probably talking a dB or two. I mean, you're not talking about like 10 dB worse. If you go from a dipole to a mag loop, you're probably talking about, I don't know, 10 dB, 15 dB worse. But to go from a resonant to a non-resonant antenna like this, you're probably talking a fairly minuscule difference. And the convenience probably more than makes up for that. So the second part of this is like, what happened to the counterpoise? And this is physics. You can't fool physics. And so there is something that the high frequency AC energy is going to be working against. So one side is going to be the radiating element. The other side is going to be something. It's going to couple to something, whether you want it to or not. And what'll happen if there's nothing in close proximity to the antenna, what'll happen is that the antenna will use the shield of the coax as the counterpoise or the ground side of the antenna. When the RF energy is going up the coax, it's actually between the outer surface of the inner conductor and the inner surface of the shield. That's essentially where the RF energy is passing up through the transmission line. When it gets to the feed point, what happens is that the counterpoise becomes the outer surface of the shield. So it's kind of like a coaxial dipole at that point. And so you do have a counterpoise, and that's why these antennas work at all, because we're using coax, and it's that outer skin of the shield that is becoming the counterpoise. Now, is that good or bad? Well, does it work or not? The answer is yes, that will work. But there's a lot of caveats. If you're running really low power, this technique works very, very well. It really with no issues. 5 watts, maybe 10 watts, no big deal. If you run a station like this at 100 watts, then depending on the length of your feed line, and the kind of equipment you're using, you may cause a bunch of problems, because you're going to get RF current flowing down the shield headed back to your radio. So if you are operating at 100 watts, you may have a significant amount of RFI coming back to the radio, which will either cause the radio to either potentially overheat, but more likely even affect the radio, shut the radio down. I mean, I've seen radios literally power off with that much energy coming back towards them. You might induce RFI into other objects close by, like speakers, or like a friend of mine went camping, did this whole thing, and his HDMI video monitor would wink out every time he transmitted, because there's current close by the HDMI cable, and it just wouldn't work. So that is an issue. So for those of us who are taking 5 watts or 10 watts backpacking, no sweat. 100 watts, field day, bunch of other gear around you, bet on having problems. Where that breakpoint happens, is it at 5 watts or 50 watts or 100 watts? Your mileage may vary. You just have to, set it up and see what happens.
So
now,
George, what can we do to mitigate that? Because that's, you want that counterpoise to be there. You may want to run a little more power. Yeah.
There's 2 things you could do. So good question. Good straight man, Rod. So the first thing you could do is you could put a common mode choke in the middle of your feed line. So what the common mode choke does essentially is it attenuates the common mode currents, those currents running down the shield heading back to your radio. When they hit the choke, they'll be attenuated significantly. They'll be attenuated like 30, 40 dB. So that's enough to make them essentially invisible to the radio for the most part, even at 100 watts. So let's say if you're running 25 feet from your radio to the feed point, if you could take that 25 feet of cable and break it in half and put 2 12-foot lengths and stick a choke in the middle, what'll happen is the upper 12 feet of your feed line will be the counterpoise. And then after the choke, that signal will be tremendously attenuated and essentially eliminating it from feeding back into the radio. So that would be the first thing I would do, the most effective thing. This is a case where actually having more feed line might be to your benefit, because you do want a reasonable length of counterpoise. How long a counterpoise do you need? Well, there's no magic number. You could say however long the radiating element is would be a similar answer for your counterpoise, but obviously it depends on how much coax you want to use. for me, typically 20 and 40 meters. I want at least a dozen feet before I hit the choke, and longer the better, maybe 25 feet. I tend to make coax chunks in 10, 20, and 25 foot lengths. So I might run like 20 feet from the choke to the antenna, then another 10 or 20 feet to the radio. Now, the other thing, yeah, shoot.
The choke, one interesting, is that also classed as a line isolator?
Yes. So a choke, a line isolator, sometimes called a current balun. Those are all the same thing. They're all fancy and cryptic names for a very simple concept. It essentially, the way you make the choke, there's a lot of ways you can make a choke. The way I make the chokes is, again, I'm going for small and effective. So if you look at the thing on the far right-hand side here, that's a common mode choke. So it's essentially a ferrite core with coax that's wrapped around that ferrite core about 12 to 14 times. And depending on the mix of the ferrite and the number of turns of the coax, you can kind of center the optimum frequency, but they're very broadband. So like one choke would be fine for all of HF for the most part. So this is very compact. Now you can make chokes like with big coils of coax around a big form, but that's not practical for portable use. Whereas something like this is like 4 inches long. There's nothing to it. By the way, if you were to take a look at the inverted V match on the far left, if you stripped off that black plastic covering, what you would see is the same thing. That's a balun. So the first thing is the dipole is a balun. The next two are ununs, and the last one's a choke. And so to just get the terminology right, so balun is a balanced to unbalanced matching unit. So the balanced part is the dipole, and the unbalanced part is the coax, hence the name balun. And so what that matching unit on the dipole is the same thing as the inline choke. It's physically the same thing. It's the same choke, it's the same coax, it's the same number of winds, it's identical. So for that dipole or inverted V, that little matching unit is a 1-to-1 impedance match. So it doesn't change the impedance, but it performs that choking function, and it matches the unbalanced to the balanced transmission, dipole. When you look at the ununs, the second and third one, those are transformers. They're transforming the impedance. In one case, a ratio of 9-to-1, in the other case, 49-to-1. And we'll get to why 49-to-1 in a minute.
George, before you leave that slide, one thing I noticed on your units, you have those big ears that you can wind wire around. That's really, really useful. But is there a trick to keep that wire from getting all tangled up over time?
Yeah, if you look at these, you'll notice that all of the wire looks really neat on the left and right sides. And the trick is you wind it in a figure 8 pattern. So the last thing you want to do is do an overhand like circular wrap, because you're creating twist every time you do that, and it's a total nightmare. So if you take the wire and you loop it around, let's say left to right, and at the bottom flip it around and go back and forth in a figure 8 pattern, then you won't it doesn't twist the wire, and it'll pay out very easily.
Oh, very good. Thank you.
If nothing else, that's a useful tip. Alrighty, so let me, in the interest of time here, let me zip forward. The other thing that you can do, by the way, is you could also add additional counterpoise wires at the feed point. So when I make these antenna things, I put additional banana connectors to optionally add additional wires. This is not a binary thing. It's not like if you put on a wire, it will work. If you don't put on a wire, it will not work. It doesn't work that way. What happens is whether these antennas need a counterpoise wire there or not, or if it makes any difference at all, depends on many factors. What's the frequency you're operating on? How long is the radiating element? How long is the distance from the feed point to the choke? How much power are you running? What's near the antenna that it could be coupling to? And how long are those wires if you put them on there? All of those factors will determine whether or not it makes a difference to put counterpoise wires on or not. In my personal experience, it rarely makes a difference. So the connectors are there in case you want to give it a try. But I don't bother, frankly. I don't really think it makes that much of a difference. As long as you use an inline choke, you really get the effect of what you want. If you're putting up a permanent installation and you have the room, sure, why not? But I probably wouldn't bother for the most part, but it's always an option. So let me, lastly, let me touch on the Nfed halfwave. Nfed halfwave is a completely different approach to what looks like a similar kind of antenna. A Nfed halfwave, unlike the random wire antenna, is a resonant antenna. It is designed to operate on a particular band and not require a tuner, which is a big plus. So if you're going to the field with a 705 or an 817 or an 891 or any of those radios that don't have built-in tuners, and you don't want to bother with a tuner, but you want to use an Nfed, then the Nfed halfwave is like the answer. It's mechanically very similar in the way you set it up. The way it works is that, remember, our half-wave feed point impedance is going to be in the like 3,000 ohm range. So you need to drastically bring it down to 50 ohms. So you need a high impedance ratio. So 49:1 is very common. And so that'll bring that, 3,000 ohms down to 50 ohms, more or less. And the way you tune it is you measure out a half wavelength of wire. Always start with more. It's easier to cut wire off than cut wire on. So start with a longer length. Measure the resonance of the antenna with the feed point. It'll be low because you have too much wire. And then you start snipping off wire a couple inches at a time until the thing comes into resonance at the frequency that you want. And again, being a full-size wire antenna, it's fairly broadband. So if you cut this antenna for the middle of 20 meters, it'll be great on the phone end, and it'll be great on the CW end. If you only operate CW, you might as well move it down to the CW end. It'll still work on the phone end. So again, big plus being a broadband antenna. The same rules apply to the Nfed half-wave as the random wire, in the sense that physics will find a counterpoise. Again, it'll be the shield of your coax. Again, a lot of power will come running down the coax back to your radio and potentially cause you problems. So guess what? You might want to put a choke in the line. Same story applies here. So same story with choking off the RF. Same story applies to putting on counterpoise wires if you feel like you have the need for that. These antennas are super useful for virtually every kind of portable radio, because no tuner required. A half-wave antenna will work on its fundamental frequency. So let's say you cut this for 20 meters, 33 feet long. It'll work on 20, and it'll work on even harmonics. So a half wave, 1 wave, 1.5 wave. So a 20-meter half wave will work perfectly fine on 10 meters. If you cut it for 40, it'll work perfectly fine on 20 and 10. The other thing you might want to do is think about making a system. So one of the reasons for those link dipole links is you can use the same technique to extend the lengths of your random wire antennas or your Nfed half waves. So you might, for example, take your Nfed half wave, cut it to 20 meters, and then take another chunk of wire about 32 feet long, put some banana connectors on the end of that thing, wrap it around a different wire winder, and you can stretch out your 33 feet on 20, and you can link on another 33 feet and make it a 40-meter antenna if you have the space. So for very little money and space, you can have a whole set of antenna elements to snap together to work in this with the same feed point. So it's really cool. The way we manufacture the antennas, we supply a piece of wire, like on the random wire, it comes with 29 feet, and on the Nfed half wave, it comes with about 35 feet, and you snip it to 20. That wire is soldered to the circuit board and strain relief through the circuit board, but there's a banana connector on the circuit board, so you can cut your own wire and plug it in and use a clip for strain relief. So you can have a whole, array of little wire elements you can tack in there.
I have a question.
Yes.
Yeah, the 49:1 balun. One question I would like to ask, and I'm sort of slightly deviating here.
By the way, it's not my mistake.
It does usually put 100 puff capacitor across, don't they, on the input?
Yes.
The rating of the voltage for the power that you're using. So I mean, I'm running 400 watts. Let's say I'm running 400 watts into something like this. Then would sort of 3 kV power rating for the capacitor be adequate, or would I have to?
You're in the ballpark. So we rate these feed points at 100 watts. I've never run more than 100 watts of these, and the component sizes and values are intended for 100 watts and less, since they're really meant to be portable. And so in that case, we put a 1 kV cap on there, because the calculated maximum RF voltage is around 600 volts. Right. So at 100 watts, so 1 kV is kind of a good headroom. If I were running 400 watts, then I would imagine probably 3 or more. I mean, I don't know what the increments are above 1 kV, honestly, but I would think 3 is probably ballpark fine.
Thank you for that.
Yeah.
Thank you.
Bigger is always better in that case. You can't go wrong having a bigger one if it's convenient. So if there was if you had like 3 kV or 5 or 10 for, and it wasn't that much bigger or more expensive, I get the bigger one. But 3 should be okay.
You'd use a Type 43 core.
Yes, you could use a Type 31 or 43. I use 43s.
Yes.
Comment, George?
Yeah.
Okay.
This particular issue of Nuts and Volts, which I imagine some of you get, has a very nice little article, or practical level article on the Nfed half-wave antenna. I just found it well written. And he also advertises this little 49-to-1 Ballon, which is readily available for $10, all built. I bought one. It works very well. It's a 49-to-1 or 7-to-1 ratio Ballon for the Nfed resident long wire.
Yeah, so these are great antennas. If you want a good build project or like a club project, these are great because there's very few parts. They're relatively cheap. You can build it in an evening. If you built one, the second one you can build in like 20 minutes. I mean, so these are pretty quick builds. Let's see, I mentioned all the YouTube stuff. So this shows you that what you just showed, John, the 49-to-1. This is basically the construction. What you're really building in the transformer is to get the 49-to-1, you have essentially 2 turns on the primary and another dozen turns on the secondary. The primary is what's called a bifilar wind, which is just a fancy way to say twist the wires together. And then just wrap the wire around the core and off you go. So there's really not much to it. Very easy to build. This was the prototype, the first one that I built, and I put it on my fancy schmancy MFJ antenna analyzer. And in the middle of the 20-meter band, it was 50 ohms and a 1.0 to 1 SWR, which made me question whether or not my meter was working properly. It just seemed a bit too optimistic, but I'll take it. So you could do all kinds of fun stuff with this too. Like I was playing around with mechanically shortening that 40-meter half wave, because again, if you have a 40-meter half wave, it'll work on 20 and so on. So I took the 66 feet of wire. I took a bunch of other enameled wire, wrapped it around a 1-inch piece of PVC, like 30 turns, to shorten the thing mechanically. And of course, it resonates on 40 and 20, and it's mechanically shorter. It is a little bit less efficient. It starts to violate George's rule of efficiency in high Q or low Q antennas, but it's fun to play with this sort of stuff. One last thing, there was a project that I did a couple of years ago. I have not gone back to this just because I had other things to do, but being the lazy sort that I am, I like the idea of the link dipole, but didn't want to spend the 3 minutes it took to pull it down and change the link if I were changing bands. So I thought, why not make a wireless remote control like you do? So I designed this little circuit board that you can clip where that mechanical link goes. And so I put a microbit microcontroller on there and a relay. And so I made these things so you can put a button on the controller. So you have an open and a close button that remotely opens and closes the link. So you can save the 6 calories you would burn taking down the antenna. And then later on, I found an even better way to do it, which is this little microcontroller thing on the picture here. This is called a JDY40. I don't know what they made these things for. I think it's like the remote control talking Barbie. And the way it works is you can set this thing up to be a receiver or a transmitter. And if you pull any of the control pins to ground in a certain mode, it transmits a signal to the other one and pulls the corresponding pin high or low. So it's very simple. Button on this side goes to a buffer to actuate a relay on the other side. And so I made a new version of this that was more compact with a smaller battery and these little things. And it actually works great. You get about a 30-foot range from it. So if the links are up, a dozen feet, 20 feet off the ground, you're not gonna be more than 25 feet away, and you just hit the button and it goes from 20 to 40 meters.
So George, you ought to put a super cap in that thing and harvest the power from your transmitter to charge it, right? So then you don't need to. Don't need the battery, right?
That's an excellent suggestion. Yeah, actually that, and I also want to put an LED on there and rectify the RF so it winks and blinks as you're modulating. So you get that, the halo effect. So anyway, that's the whole story. Let's see. Oh, this is some other stuff. Anyway, that's that. So I guess my summary to all this is that these antennas are funny, like having quite this renaissance and resurgence of interest in these things because they're so simple and they really are pretty darn effective. And I think for portable operating, it's really kind of hard to beat them. And every time I see somebody pull out a big, heavy portable antenna that's compressed, I think, wow, you're really missing out here, because for something less expensive and more portable, you can actually get better performance. So, why don't people do that? Oh, one last thing. I'm sorry. I know this is on like 2x over time. I have been experimenting with fiberglass mass versus carbon fiber, because carbon fiber mass are like a third the weight of the fiberglass equivalent. And they're also like more expensive by quite a bit, the good ones. And so there's a real question in my mind as to whether or not you could use a carbon fiber mast, because obviously for very portable, like backpacky kind of stuff, then the carbon fiber mast would be way better. So I kind of poo-pooed this notion that it would be a problem. And so I set up the carbon fiber mast, and I did my usual Nfed random wire up the side of the mast like I do with a fiberglass pole. And what I found was that the carbon fiber mast really detuned the antenna. And the weird thing was it didn't like shift the frequency of the antenna. It screwed it up kind of entirely. It was just too much coupling into the carbon fiber, much more than I had expected, frankly. And so I was really bummed out. I mean, the sad thing is it's too good of a conductor and it will screw up your radiation, but it's not good enough to actually use it as an antenna. It would be awesome if you could actually load up the carbon fiber mast itself. That doesn't work. So it's really kind of annoying. So here you have this great, super lightweight, very strong material, but you can't really use it in a conventional vertical. But what you can use it for is, if you think about it like a metal mast, you can certainly use it as a support for a sloper or a V. So not an inverted V, but as like a long wire, Nfed V, where you're kind of holding the thing up with the carbon fiber. So that's probably the best lightweight option, is a carbon fiber mast, but don't run it as a traditional, radiating vertical element. Use it as a support. Yeah.
So I think I shared this story with you when you went through this little nightmare you had. And the story was that I was asked to do the RF system for a carbon fiber drone. And I get there and said, well, you can hide all the antennas inside the airplane, can't you? I went, not if you made it out of carbon. And yeah, well, we're not getting much, range on it. We want you to look at it. And well, sure enough, and exactly what you went through. So it's a nice RF sponge.
Yeah, it really is. Irritatingly. And Jim, I really appreciate your backdrop, because it's very appropriate for today's topic, with a trailing wire coming out the back of your dirigible.
George, a question you mentioned with the carbon fiber that you could use it as a V, but not an inverted V. I'm wondering why it would work for a sloper, but not for an inverted V.
That's a great question, John. So the carbon fiber masts that I was playing with are really like these fishing poles, where they go down to a really tiny whip at the end. So there's just not enough rigidity to support the inverted. You need about a 1/2 inch diameter to support the feed point for the inverted V. So you absolutely could use a carbon fiber. There's absolutely no question you could use a carbon fiber mast as a support for an inverted V, if it's big enough. It's just the one that I have is like super small and whippy, and it's just not mechanically big enough to hold it. But like, for example, when we set up for field day and use a carbon fiber mast, we could put an inverted V off that and it would work fine, because those things go from 2 inches down to about 1/2 inch. or 3/4 of an inch. So that's plenty rigid enough. The carbon fiber mast I was playing with for this test was like a fishing pole. And so it starts out being like 3/4 of an inch in diameter and goes down to nothing. So that's just not stout enough to hold up the feed point.
Thank you.
But it'll hold up the wire, you know, it'll bend over, but it'll kind of hold up the wire.
Yeah. Dan, I think I cut you off there. Did you have a
Yeah.
question?
Yeah, well, no, not a question, more of a comment than anything else. So I've been actually going the exact opposite direction as George, not caring about weight at all. But when I moved into this house a year and a half ago from Seattle area, I needed an antenna that I could put up really quick and dirty before I could get a tower mounted. So I looked around and I found these little Nfed halfwave antennas, and 4,000 contacts later, I mean, I really like the antenna so much so that I'm incorporating it into the final antenna farm that I'm putting together here. And the only thing I didn't like about the commercial bought ones was that I couldn't run them at legal limit. So this is a 49-to-1 auto transformer, built essentially the same way that you described there. The big difference is that it uses 14 gauge wire and 3 mix 52 cores, because I tried the 43 cores and it just didn't work well for me. So I went to a mix 52, and I put a 100 puff 20 kV cap across the across it, and about 133 feet of wire. And boy, I mean, the thing plays, and you're right, they turn out to be a little long, so you have to trim them back once you get them installed. But I have a 47-foot fiberglass mast here I just got it this week, and I'm going to be putting it out about 100 feet away from my shack and feeding it with coax, so I don't have a radiator sitting next to me, for the very reason you talked about, the counterpoise and all of that. So I've just been thrilled with this Nfed halfwave as an antenna, and I'm really surprised people don't use them more, because they're, for people who live in HOAs, which I don't, thankfully, but I mean, they're very stealthy and easy to put up. So that was a great presentation. I learned a lot. Thank you.
Oh, my pleasure.
Right.
Yeah.
Are you aware that you've got about a 1 kilohertz square wave on your audio?
No,
Yeah.
I'm not aware of that.
And it's only when you lean into the mic, Dan.
Yeah, I was slacking you about it, Dan.
Oh, you were? Okay.
Yeah, when you lean back, it goes away.
I got to go on a bug hunt then. All right. Thanks.
I don't know what you plugged yourself into, but your proximity to your microphone is not going well.
Is that any
Alrighty.
better?
No.
Did it go away? It's still
No.
there.
Yeah, we can work on it later.
It's from the COVID implant.
Okay. So any other questions, folks, for George?
That George, that little wireless link relay thing that you were showing, does it come with a relay, or do you add a relay to it?
You have to add a relay. So the only thing that's on the board is some AAA batteries, the RF module, and then a small surface mount latching relay. So the only time the current's consumed by the microcontroller, and when you actuate the relay, there's just a little bit of current to pulse the relay on or off. So there's no holding current for the relay required. And I'm just using a little telecom relay. It's a 2-amp relay. One of the questions in my mind is like, how high of wattage would that little telecom relay support? I mean, you can use the same concept with a big relay to work fine, but there's more mass and weight. So
probably quite a bit.
Yeah. So I think with these small relays, it's perfectly fine at QRP, maybe 20 watts. At 100 watts, probably okay, because the antenna elements are resonant. If the antenna elements were not resonant and you had a high voltage point, that might be an issue. But since they're resonant, probably not.
But what happens if you don't have Jim Zeppelin?
The Zeppelin does give you a 12 dB advantage, I think.
There you go. So any more questions for the slides or for George's presentation?
Yeah, when are they in stock?
Remember, this is not sponsored by.
Yeah, this is this wasn't supposed to be a ham radio like product. It was just I was just making it for my own fun, and then I showed it to some folks and they wanted them, and so now I make them and sell them. So like I need another thing to do, like a hole in the head. But it's really a lot of fun when people use them and send you pictures of how, like the guy who's jumping out of the airplane. I mean, what a kick to have him jump out of the airplane with your antenna. You just hope to God it doesn't get tangled in his chute, but that's another story. So we have them assembled at a commercial fab assembly house. We don't do it. I mean, that'd be insane. So I just buy all the materials and send them to the assembly house. They make them up, and then we ship them. And what happens is I think, who in the world is going to want this thing? And so I make some, and then we sell them all. And then I'll make some more. And then like surely everybody who ever wanted one will have bought one by now. We sell them all. And so we keep going through this cycle. I mean, so it's kind of it's a blessing and not a curse, but it constantly shocks me that we sell out of these things. And right now we're almost sold out. Actually, we're sold out of like half of them. And so I have a whole pot of
make that little wire winding frame yourself?
Yeah, I have them fabricated.
Oh, there. Okay.
Yeah. So sure. I designed the board, and picked all the materials and built them and tested them and all that stuff. And
I was wondering if there was a 3D printed pattern.
No, but I mean that'd be trivial to make.
Oh, of course it would.
Yeah. Yeah, the reason that we use it as circuit board material is it's, like I said, I know how to make one, but they're fairly rigid, and the components solder to the board and the connectors solder to the board, and it's all very compact, and it makes it pretty reliable that way too, as it turns out.
I want to know when there's going to be a mashup when Mike Walker actually takes Jim's dirigible, but he does it as a drone and flies a Pactena behind a drone in some circular pattern and makes some calls.
He better have a ZEP antenna on the back of it, or it won't be a real ham radio.
Just use the airplane.
Okay, well, with that, I'm going to end the recorded part of the session on YouTube. For anybody watching YouTube to the bitter end, we've got some additional presentations coming up all the way from the Long Island CW Club through Mike Walker talking about remote, doing an actual live demo of remoting his station. So that's
we decided that's what it was, right?
Well, it's a high wire act. Come on.
Because at midnight last night we weren't done yet.
And we've even got some folks coming from the ARRL to do a presentation for us as well. So good stuff coming up. With that,